Good morning, everyone. My name is Thamer Al-Zuriqat, and I'm from the Hamburg University of Technology. And today I will be presenting to you our research about detecting damages in lightweight bridges with traveling masses using machine learning. So as a little bit of a topic background, lately we are using more and more lightweight materials to build structures, and specifically bridges. And those materials have some unfavorable structural dynamic behavior. And sometimes we have vehicles running over a bridge with a more mass than the bridge itself. And in general, we can say that the traveling mass problem represents a non-stationary structural dynamic problem. And in its simplest form, a lightweight bridge with a traveling mass can be modeled as a continuous Euler-Bernoulli beam. And this Euler-Bernoulli beam, or the equation of the beam, considers inertia forces of the vibrating beam as well as the traveling mass. And what differentiates the traveling mass problem from the regular problem is something called this contact force. And we can estimate this contact force by considering equilibrium at the contact point between the moving mass as well as the bridge. And when we consider equilibrium, we will have something called, or the equilibrium can be expressed as a total vertical displacement. Now this vertical total displacement is a composition or the summation of the vertical displacement itself plus a component coming from the surface roughness. And this surface roughness is what we need to look at, because this is what caused the vibration in the first place. And if we have a perfectly smooth surface, when a mass is moving over a bridge, then it will not cause any vibrations. So if we look at this equation, we see it's from the second order in time and fourth order in space. One way to deal with this equation is by doing something called an eigenvalue decomposition. And for this eigenvalue decomposition, we can calculate this W, the deflection, or the vertical displacement. And this vertical displacement is a convolution between the space function phi and a temporal function called q. And it's also the summation for all the eigenfrequencies from the first to the infinity eigenfrequencies, but for our civil engineering application, we mainly consider the first 2 or 3 eigenfrequencies. In our case, we took the first 2 eigenfrequencies. And then we can reach to this equation of motion matrix, and one way to solve it is from the second degrees by using space-state formulation. And for this space-state formulation, also one way to deal with it is by using an eigenvalue analysis. And for this eigenvalue analysis, we can go back, but we can do this eigenvalue analysis for every kappa or instant in time. Then we get the value of q, and we substitute it, then we get the deflection. Then at the end, this deflection or displacement, if we derive it once, then we have a velocity, and if we derive it another time, then we have an acceleration. And this is what we need, because the acceleration will be used in something called the Galbert transform. And this Galbert transform is as any transform in the world. It changes the data from one shape to the other. And in here in this case, it changes the data from the time domain to the time frequency domain, where we can see the natural frequency or the fundamental frequency of our data. And we can also generate these colorful images that we can use as an input or to train our classification model to detect damages in bridges. However, when we want to train an artificial neural networks or a convolutional neural network, we need a lot of data. So how do we do with it? The way is to go as simple as possible. So we want to have a situation or a use case where we have a simple use case as much as possible. So we chose to have a steel beam. And for this steel beam, we know the modulus of elasticity, we know the moment of inertia, we know the density. So we can model this beam and generate as much data as we want. However, before modeling the data, we need to know where do we want to install our sensors in real life, so we can take the data exactly from the same locations in the analytical model. So we chose to put the sensors at the first quarter, the last quarter, as well as in the mid-span, more or less. And then here we created the analytical model. And for the analytical model, we need also to introduce or to know what damage scenarios we would have. So we decided to have 5 damage scenarios, as well as a scenario where we would have an intact beam. And for this intact beam, it's the totally or perfectly healthy beam, so nothing is going on. And for these 5 damage scenarios, we want to, one way, for example, here in the middle when we have a crack, one way to simulate it is by putting a rotational spring in the span. And to simulate a damage at the support, we can put a translational spring at the support. And we define in our criteria that this damage should represent a 7 to 10% drop in the fundamental frequency in our data or in our result. So now there is too many factors to consider when doing simulations. So one of them is the mass, the value of the mass, the velocity of the mass, the rotational spring stiffness, as well as the translational spring stiffness. And to know how many simulations you need to do, you can use something called a hypercubic sampling. And then for our case, we wanted to have 500 simulations per damage scenario. And in a total, this would result for our 6 scenarios, we would have 3,000 simulations to run. So this is an example from the data. And you can see here the damage scenario L0, which is the perfectly healthy beam. And here is the damage scenario L1, where you have a crack at the first quarter of the beam. We can see a drop in the natural or the fundamental frequency in the collected data. So now what we can do, we have a lot of data. We can use this data to train a convolutional neural network. So we take the 3,000 images, we input them to a convolutional neural network with an input layer, convolution layer, pooling layer, and flattening layer. Afterwards, it goes through a fully connected layer that connects the neurons of the flattening layer with all the output layer or the damage classes. And for the training, as I said, we used those 3,000 images, and we split them as the usual way to do it, 80% to train and validate the model, 20% to test the model, and we used during the training an Adam optimizer, and we set the learning rate to 0.001 with a batch size of 36, and then we concluded the training after 7 epochs. Now, we used the testing data to evaluate our model, and as you can see, it's a perfect fit, and it's the accuracy of the model. This is data that the model never got to see before, and it's really good result, and it makes you wonder, does the model or is the model overfitting to the simulations? So one way to check your classification model is by using some or doing some laboratory tests. And in those laboratory tests, we have the beam, of course. So we installed a motor that drives a pulley and moves the mass, and we recorded these acceleration data from the points that I showed you before, and here is our professor in the background. And then for these, we had different scenarios, so we had different mass values, we have different velocities, and at the end we managed to simulate the damage scenario L2, L4, L5, and also we have, of course, the perfectly healthy beam. And we had in total 30 cases per scenario with a total of 120 cases. So now we can take these data, throw them into the convolutional neural network, and see how it would behave. And the results from all 3 locations is very acceptable, or very good actually, except in the location S2 where it's the damage scenario L2. And this could be attributed because if we think about the mood shape of the beam, and at the mid-span, it's a 0 crossing point in the second mood shape, as I said. And also the crack at the mid-span as well is not as significant, and it cannot be distinguished from the intact beam. So as a conclusion, we used machine learning to analyze the unconventional structural response of lightweight bridges with traveling masses. We used convolutional neural networks trained with data obtained from analytical models to classify data into predefined damage classes or scenarios. And then this CNN has been tested with data took or obtained from the laboratory, and it showed a satisfactory results, except in one case where we have a damage scenario L0 and damage scenario L2, where it got misclassified. So for our future work, we want to apply our approach for real data or data from real structures, and we want also to implement our approach in a decentralized manner in sensor nodes. Thank you for listening, and if you have any questions, let me know.